Lesson: Machine learning versus traditional algorithms, risk implications. Machine learning and traditional algorithms represent two distinct paradigms in the field of computational problem solving and data analysis, each with unique risk implications. Understanding these differences and their associated risks is crucial for professionals involved in risk management, especially in the context of emerging technologies such as blockchain and artificial intelligence. This lesson delves into the nuances of machine learning versus traditional algorithms, emphasizing actionable insights, practical tools, and frameworks that professionals can implement directly to mitigate risks and enhance proficiency in managing these technologies. Traditional algorithms are rule-based systems that follow a specific set of instructions to solve a problem. They are deterministic, meaning they produce the same output for a given input every time. This predictability is advantageous in scenarios where consistency and reliability are paramount. However, traditional algorithms often fall short in handling complex and unstructured data, where patterns and relationships are not explicitly defined. In contrast, machine learning algorithms excel in such environments by learning patterns from data and improving their performance over time without being explicitly programmed. This adaptability makes machine learning particularly valuable in tasks such as image recognition, natural language processing, and predictive analytics. Despite their strengths, machine learning models introduce unique risks that differ from those associated with traditional algorithms. One primary concern is the black box nature of many machine learning models, especially deep learning networks, which can make it difficult to interpret how decisions are made. This opacity poses significant challenges in ensuring accountability and transparency, particularly in high-stakes domains such as healthcare and finance, where understanding the rationale behind a decision is crucial. Moreover, the reliance on large datasets for training machine learning models raises concerns about data privacy and security. The potential for bias in training data can also lead to biased predictions, perpetuating existing inequalities and causing harm in sensitive applications. To address these risks, professionals can employ various practical tools and frameworks. One such tool is the LIME framework, which provides interpretable explanations for individual predictions made by complex models. By approximating the model locally around a specific instance, LIME allows users to understand the factors influencing a particular prediction, thereby enhancing transparency and trust. Another approach is the use of adversarial training techniques to improve the robustness of machine learning models against adversarial attacks. These techniques involve systematically exposing the model to perturbed inputs during training, thereby strengthening its resilience to malicious attempts to manipulate predictions. Data privacy and security concerns can be mitigated through techniques such as differential privacy, which introduces noise to the dataset to protect individual data points while preserving the overall utility of the data. This approach is particularly relevant in environments where sensitive information is involved, such as healthcare and finance. Additionally, federated learning offers a decentralized approach to model training, allowing models to be trained across multiple devices without sharing raw data, thereby enhancing privacy. Bias in machine learning models can be addressed through careful dataset curation and the use of fairness-aware algorithms. Tools such as IBM's AI Fairness 360 provide a suite of metrics and algorithms to detect and mitigate bias in machine learning models. Implementing these tools involves a step-by-step process. First, assessing the dataset for potential sources of bias, then applying pre-processing, in-processing, or post-processing techniques to reduce bias, and finally, evaluating the model's fairness using established metrics. The deployment of machine learning models in real-world applications also necessitates ongoing monitoring to ensure continued performance and compliance with ethical standards. Model drift, a phenomenon where the model's performance degrades over time due to changes in the underlying data distribution, is a common risk that requires proactive management. Implementing a robust model monitoring system that tracks key performance indicators and triggers alerts when anomalies are detected is essential. Tools such as TensorFlow Extended provides scalable solutions for model monitoring and lifecycle management, enabling organizations to maintain the reliability and accuracy of their machine learning systems. The integration of machine learning into blockchain systems presents additional risk implications. While blockchain offers enhanced security and transparency through its decentralized and immutable nature, the combination with machine learning introduces complexities that require careful consideration. For instance, the reliance on smart contracts, which are self-executing contracts with the terms of the agreement directly written into code, necessitates rigorous testing and verification to prevent vulnerabilities and exploits. Formal verification techniques, which involve mathematically proving the correctness of smart contracts, provide a rigorous approach to ensuring their security and reliability. Furthermore, the scalability challenges of blockchain systems can impact the performance of machine learning applications. Solutions such as sharding, which involves partitioning the blockchain into smaller, more manageable pieces, can enhance scalability and improve the efficiency of machine learning processes. Implementing these solutions requires an in-depth understanding of the underlying technologies and careful consideration of the trade-offs involved. In conclusion, the contrasting risk implications of machine learning and traditional algorithms necessitate a comprehensive approach to managing these technologies. By leveraging practical tools and frameworks, professionals can enhance transparency, improve robustness, ensure data privacy, mitigate bias, and maintain the reliability of machine learning systems. Moreover, the integration of machine learning with blockchain technologies presents unique challenges that require specialized knowledge and strategies. As the landscape of AI and blockchain continues to evolve, staying abreast of the latest developments and best practices is essential for professionals seeking to effectively manage the risks associated with these transformative technologies.